So we have seen how a B0 field gradient can be used to spatially encode the frequency of the spins along the direction of the applied gradient. And together with a frequency selective RF pulse, we can select a particular slice of spins. We can use this same idea to spatially encode the signal from within this slice of spins in each direction. If we were to detect the signal while at the same time apply a field gradient along one of the directions within the plane of the slice, then we would expect that the signal will be encoded as a function of position along that gradient. This is known as frequency encoding, and the frequency encoding gradient is also known as the read gradient. This spatially encoded signal will therefore consist of a projection of the signal from all the spins that are in the same position along the read gradient direction. So if a Fourier transform is applied, the result will be a projection of the shape of the object against the direction of that gradient. This is best illustrated with an example. We have three samples of water arranged in the magnet. A field gradient is applied along the horizontal direction. The frequency of the spins within the samples are therefore different and are encoded with increasing frequency from left to right. So the signal from each of the samples will occur at different frequencies, and within each sample, the shape of the signal will be a projection of the spin density against the horizontal axis as shown here. You can see that the projection reflects the shape of the object. If we now change the direction of the gradient to the vertical axis, then again the signal will be a projection against this axis, which looks like this. The projection is the sum of all the signals at each point along the gradient direction. So here, the large sphere and the cube are superimposed, and their signal intensity adds together. We can apply this gradient along any direction in the plane of the slice, and the projection will change as a function of the direction. For simplicity in this animation, rather than rotate the direction of the gradient, we rotate the sample and show the projection along the horizontal axis as the sample rotates. The projections obtained in this way can be used to back calculate the original shapes of the three objects in a manner very similar to that used in CT imaging. This technique is known as back projection reconstruction and was one of the first proposed MR imaging methods, for which Paul Lauterbur received the Nobel Prize in 2003, together with Sir Peter Mansfield, who invented the slice selection method we described earlier. Back projection reconstruction is not used routinely in MRI systems today. Instead, the second orthogonal direction in the slice of spins is also spatially encoded with another gradient, and a Fourier transform is applied along each direction to produce a two-dimensional image. We have encoded the spins along one direction with the read gradient. The orthogonal direction can be spatially encoded by applying a gradient in that direction before the read gradient. This second gradient will also encode the frequency of the spins along its direction, but this time the encoding is performed before the signal is detected and alters the so-called phase of the spin vectors as a function of their position along that gradient direction. This gradient is therefore known as the phase encoding gradient. How does this work? Here we have two spheres of water, and we show the projection of the samples along their horizontal or read direction. If we measure a series of projections, each time applying a phase field gradient for a short time before acquiring the signal, then each point of the projection that we observe will have an intensity and phase change according to the position of the spins along the orthogonal gradient direction and according to the strength of the field at each position. Here, the phase encoding gradient is 0 and then increases for each successive projection. You can see the intensity change along the projection as a function of the phase gradient strength. If we were to plot the intensity of the same point in each projection, then we would observe a signal which contains all the frequencies that contribute to that point from the direction orthogonal to the read gradient, as shown here. So if we then Fourier transform this signal then the result will be a spatial profile of the sample along the orthogonal direction at that point. So if we transform along each point of the projection, then we build a two-dimensional map of the spins showing the intensity of the signal from each position in the slice. This represents an image of the slice of water molecules in 2 dimensions. So we now have spatial encoding of the spins in 3 directions. A slice gradient, together with a frequency selective RF excitation pulse, creates a slice of spins with a certain thickness and position. A gradient in the read direction encodes the signal as a function of position in one direction of the slice plane to produce a projection along that direction. The phase gradient then encodes the projection intensity and phase along the orthogonal direction in the image plane.